Let's continue on our journey of identifying hazards, analyzing risks, and then defining controls for them. The next thing that we will be talking about on this journey is how to characterize a hazard. In other words, how to understand the properties and the possible behavior of a hazard and how it could harm us. Because if we don't understand how this hazard can behave, then we cannot control it. Remember our summary a little bit earlier. Firstly, if I cannot see that hazard, then I can't give it a name. I can't identify it. If I cannot identify it, I will not be able to analyze it. And if I don't analyze it to understand it, then I will not be able to control it. And if I can't control it, sooner or later, it is going to cause me some harm or injury. If you are not used to the environment in which you are doing a hazard identification risk assessment, then you will probably not see or recognize the hazards as objects or as something that has the potential cause harm. So if you're working in a technical environment and I suddenly move you into a commercial kitchen or into a restaurant, you will not be able to identify all of those hazards and you will not understand those hazards. For instance, some of the bacteria and some of the unhygienic conditions and stuff that will exist, or what happens if we reuse cooking oil too many times. The same is true if you are in an office environment or in a restaurant environment and I suddenly now put you on a construction site or in a building project. You would not recognize the tools for what they are, and therefore you would not be able to analyze them. So, very important to be able to identify the tools. And remember, you don't have to do it alone. You can use experts in that field. You can use people that know the technicalities of that facility or that operation. You might know the process, use their brains and their experience and their knowledge so that you can identify the hazards. Here's a picture of 3 unmarked bottles of liquid. Question to you. When you are offered one of these bottles, will you open it and drink it? I would not, because I don't know what is in there. There are certain familiar colors, but I have no idea what is in there. Is it colored water? Is it alcohol? Is it cold drink? Is it acid? Is it poison? I don't know. Before I can drink any of that, I need to understand what is in that bottle. Now, how would I find out what is in the bottle? I said previously, one of the ways that we can characterize incidents or that we can see and analyze hazards is with our 5 senses. I can taste it, I can smell it, I can look at it, I can feel it, and maybe I will find out that one is cooking oil, another is brandy, and maybe the other one is water in the green bottle. I don't know. But it could also be dangerous for me to just taste the stuff, because some poisons are poisonous enough that if I just get a little bit on my tongue, I can already get sick or hurt. It could be a corrosive substance like an acid that I don't want to get on my skin or in my mouth. It could be an oily substance that I can feel with my fingers, but I don't know. So for me to be able to make a decision, am I going to drink this? Am I going to give it to my children? Am I going to use it for cooking? Or am I going to throw it in the drain? Or what am I going to do with this? I need to find out what is this. And when something like this has got no characteristics, it becomes very, very hard for me to analyze and characterize it, and then to put the control measures in place. Maybe some of the stuff the children can drink, maybe you don't want that anywhere close to your children. Maybe that is stuff that you need to use in your car engine. Maybe that's something that you can use in food. We don't know. Might be so dangerous when you open up the bottle, something comes out, and already you get sick because you didn't get the right PPE to protect yourself against the fumes or something like this. So it's very important to understand what we are dealing with. The moment that something has got a label on, or it's recognizable, then I can actually say, well, this is Johnnie Walker Red Label. And hopefully the bottle is sealed. Otherwise, somebody might have put cheap whiskey in that bottle, and then they say it's Johnnie Walker Red Label, but it isn't. I know people like that. But the thing is that I can very likely identify that this is Johnnie Walker Red Label. It's an alcoholic drink. I know what it will do to me if I drink, and if I drink too much, I know the consequences, especially if I drink and drive, or if I drink and I come to work, or if I drink too much, I know what the consequences will be in the morning, because I've been able to identify this hazard, and I have been able to give it a name, and I've been able to analyze it, and I understand the consequences, so I know how I should behave around it. The second bottle is now clearly marked as hydrochloric acid. We know that hydrochloric acid can dissolve steel and iron. It's a corrosive substance. When it gets on your skin, it will burn holes in your clothing, and it can react with certain kinds of metals, and the gas that comes off is hydrogen, and that hydrogen can burn or explode. So once I can identify it, right, I need to see it, then I need to identify it, then I can analyze it, and I can analyze it for its physical and its chemical properties. And I can then identify what is useful or what is harmful around this hazard. Here's another example of why it's important to identify something in order to be able to deal with it. On the left-hand side, we have an African python. And the way, if I say python, we immediately can do our research, and we find out that this animal will bite into your body with very sharp serrated teeth, and it will anchor its head, and then it will twist its body around you, and it will squeeze you to death. First, you won't be able to breathe, and secondly, it will crush you, and it needs to crush you, needs to break your bones, because it is going to swallow you whole, and then the acids, in the digestive acid in the body, is going to dissolve your meat and your bones and everything. And that's how it kills and eats. If I want to control this animal, I've got to make sure that he doesn't coil around me. I've got to make sure that he doesn't get his teeth into me to anchor. And if I see somebody else that's got this thing around his body and is squeezing, I need to somehow kill the snake or get the head loose, and then we need to unwrap him before he crushes this person. Sometimes when I see people walking around with these snakes around their necks and playing with them, I wonder if they realize how strong they are. I have seen people being surprised when the snake suddenly starts coiling around them, and they realize this snake is very strong. But this snake is not venomous. If it bites you, there will be no venom, poisonous stuff, going into your body to kill you. Right? So it will kill you physically. On the other hand, the snake here on the right-hand side is a puff adder. It looks similar in coloring, but it's smaller. But if that one bites you, there where it bites you, the venom that it injects into you will destroy your tissue. It will kill the meat and it will destroy the nerves and your blood. And eventually that will go rotten. It will just destroy, it will kill all the living cells in your circulation in wherever it's bitten you. And it will spread through your body, and wherever that toxin goes, that venom, it will actually destroy the tissue and your fingers, your hands, or whatever. If it doesn't get treated, it will swell. It will swell so much that they have to cut the skin, otherwise your skin will tear, and then they will try and circulate the blood and give you antivenom. And if they don't treat this, all of that meat, that whole limb, that part of your body will die, and it will go rotten and black, and it will fall off, and the septicemia, the infection, might also kill you. Two snakes, but two very different characters, and the way that they will hurt you is very different. If I want to make sure if somebody gets hurt or if you are exposed to these snakes, I need to treat you accordingly. If I think it's the puff adder or it's a python that bit you, I might think that you're going to get rotten limbs and whatever. That's not true. But if I think that the puff adder is a python and he's trying to squeeze you, but in the meantime he's bitten you, then you're going to have pieces falling off. Okay, so I need to understand the hazards that I'm dealing with. Similarly to the python and the snake, we have tools, we have equipment, we have chemicals, and each one of them has got its own way of transferring energy, of causing potential harm and injury. When I'm trying to characterize, when I'm trying to understand a hazard and the kind of incidents and the kind of injuries that it's going to cause, I can look at certain of its properties. The first one is size. I can characterize it as large, or I can characterize it as small. We'll talk a little bit later in context which one is better. Is large more dangerous than small, or is small more dangerous than large? It doesn't matter. I must just determine, and for myself, determine, is this thing large or small? I can look at the mass of this item. I'm sure some of you have gotten to a box and you think, this is a small box, I'm just going to easily pick it up. And when you do, oops, you find that there's a lot of very heavy items in there. Or you pick up a big box and you think it's going to be heavy, and then you find, oh, this is very light. It's got polystyrene cups or something in there. So, depending on the size of something, and once again, heavy is not necessarily bad, and light is not necessarily good. If it comes to objects that are going to fall, of course, you don't want a heavy thing to fall. But if there's, so you don't, if it comes to an object that is going to fall on you, then you don't want a heavy thing, of course. Then you would prefer a light thing. But if it's something that you want to hold, something down like a sail or an anchor point or a counterweight on a crane or on a forklift or something like that, then you want it to be heavy. Okay, so it's not that heavy is bad and light is good or the other way around. It depends on the circumstances. Another characteristic is density. Density talks about how much of a substance, how much of something can fit into a volume. The standard measurement is 1 liter, okay, like a 1 liter Coke. That's a liter volume, or a liter of milk. Now, if I take a 1 liter Coke bottle and I leave it let's say I put nothing else in it, there's only air in it. That bottle will have, for 1 liter, will weigh a certain amount, let's say a few hundred grams. But if I fill that bottle with water, that bottle will weigh 1 kilogram. If I now take that bottle and I take steel washers and I put them inside that bottle, you know that that same bottle will now be a lot heavier. The bottle of air is not dense enough to sink in water. It will float on top. But the bottle full of steel washers, if I put that in the water, it's going to plumps, go right down to the bottom. It's the same volume. They are both 1 liter. But the steel washers, the density of that is greater than the density of air. Now, how does this play out in real life? If there's a fire, a veld fire, and there's a wind blowing and it disperses, it blows out the smoke a little bit. Then you can still see through the smoke and you can still drive. The smoke is not dense. However, if there's a big fire with a lot of green stuff and it blows over the road, and I cannot even see the car in front of me, it is because the smoke is dense. And therefore it is more dangerous because I cannot see. But once again, it's all about context. If, sometimes people go to war and they fight, and what they do is that they use a smoke screen. So what they do is they throw a smoke grenade between them and the enemy, and the smoke blows between the enemy and myself, or between the one party and the other party, and that stops the enemy from seeing me. I can then get up and run away, and they cannot see me to shoot me. In that case, for the smoke to be dense, it's a good thing. I don't want them to then be able to look through the smoke. So, in that case, dense smoke is a good thing. But if I'm trying to drive on a road, dense smoke is not a good thing. Okay. It can be the same with gas, toxic gases like LP gas. If there's a high concentration of LP gas that has been leaking into a room, then that room can actually explode. But if there's a low density of LP gas, if there's not much LP gas that leaked out of a cylinder into the room, the density is low, it cannot cause harm to me, I can still open the windows and get rid of that. So it depends on the circumstances whether something is good. It's not just something is less dense is good and more dense is bad. Another characteristic that we can look at when we look at hazards is shape. Something can be angular, can have sharp edges and sharp sides. Sometimes that is good. If I want to have a stop block in front of my car, I can't put a round stop block there. I want a wedge so that my car can drive onto it and it can be stopped from rolling. However, if I have a ball, I want it to be round. If I want to roll something, then it's much better if I have a round shape than if I have an angular shape. I can also look at texture. Texture means is something rough or is something smooth. Now we get sandpaper, we get very rough surfaces, gravel, rocky terrain. The texture is very rough and uneven. And then we get some very smooth textures, like silk, your skin, tables, glass. Those kind of things are very smooth. Now, which one is good and which one is bad? Well, let's take a road, for instance. If you are driving on a road, do you want the road to be smooth? Yes, it's nice for it to be smooth because then my tires don't make a lot of noise and the ride is nice. But the moment that I hit the brakes, what happens on a smooth road? Then there's less friction between my wheels and the road and I don't stop so nicely. So in that case, if I want to drive, smooth is good. If I want to stop, rougher is better. If you want to sand down something that you are going to work on, let's say a piece of wood, Then you want nice sandpaper that's rough in the beginning, that you can remove a lot of material or a lot of paint or something quickly. But when you want to finish it and you want to have it nice and shiny, then you are going to use an abrasive sandpaper with a very smooth finish. Now sometimes we use things to wash with to remove the dead skin. We've got scrubbing brushes and whatever. Now, to wash certain places where your skin is very strong and thick, there you can use something with a rough texture. But when you get to some of the softer areas, like around your eyes and face and some other places, then you don't want that rough texture because it's going to hurt you. So once again, it's not about rough or smooth. It's about what context you are seeing this whole thing in. But I need to form some idea. Is this rough? Is it smooth? Is it dense? Whatever the case might be. What is the characteristic? Lastly, a characteristic about a hazard that people sometimes overlooks is the predictability. If a hazard is going to always behave in the same way, in other words, a car is always going to drive at the same speed, along the same road, at the same time of the day, and so on, then I can choose at what time I can cross the road and the car will not hit me. But if there's a car that comes by at any time at different speeds and that drives erratically, and I don't know even if it's going to stay on the road, maybe it's one of these guys that are doing drifting and spinning, where they come with the cars like this, and it's a street racer, and he might even lose control and end up on the pavement like has happened sometimes. The behavior of that hazard is then very unpredictable. How do I control an unpredictable hazard? It's very difficult because I don't know exactly what it's going to do. So I need to identify the characteristics of these hazards or of a hazard within the context. Let me explain a little bit more about the characteristic in the context. But before I get to context, I said that a hazard needs two things to be a hazard. The first one, it must have closing potential. In other words, must be able to touch you or the target. The second thing, it must have energy, and when it transfers that energy into the target, it causes harm. So I need to, whatever the characteristic of this hazard is, whether it's big, small, light, whatever, I need to identify how that hazard is going to transfer and contact with the target to cause it harm. We'll expand on that a little bit later. Here's an example of an adult carrying a large box. And that stops him from seeing where he is going. So in this case, the large box, the size of this box, it's not very heavy, but the size of the box makes it very harmful because it's going to stop him from seeing it, and then he will fall and trip. So the incident that we're looking at is a bumping or a slipping and tripping and falling incident because that box is preventing him from seeing. The second picture, we've got a small thing. Now, this adult carrying the box, it would probably have been better for him if he was carrying a small box. So in that case, small would have been better than large. Now we look at the baby sitting on the right-hand side. What is she holding? She's holding a dice, and she's actually got quite a few in front of her. Now, any of you that have had experience with babies, you know that one of the first things they do is they put these things in their mouths. It's their way of experimenting, of finding out what this is. Now, small objects present a great danger to babies in that when they breathe in or they don't control themselves nicely or they catch a fright, then that object is small enough to go into their airway and they can then suffocate to death. So we normally try and keep small things, small enough things that they can put it in their mouth and possibly swallow it. We keep that away from children. So in this case, large is better than small because large stops it from going in the mouth, small goes into the mouth and the airway. So this just tries to explain to you how the physical characteristic of a hazard per se doesn't make it good or bad. The adult would have preferred a small hazard, a small object, a box. The child should have had a larger hazard so that he cannot swallow it. Let's talk about another characteristic and the context. Both of these things are balls and they are used for different things. The one on the left used to be used, they used it in war. It was a weapon. So it's a heavy ball and it's got spikes on it and you swing it around and then you can knock somebody and kill him and hurt him and whatever. It used to come on a stick like a whip. Now, if you want that item to kill people, you would prefer to have nice big spikes so that it actually can do the harm. That's the work of this thing, right? And the energy that you want, the energy that you're going to put in this hammer, in this ball, you want it to be transferred to the other guy and you want him to get hurt so that he doesn't come and kill you. But if you are going to play volleyball and soccer, you wouldn't like to have a ball like this, would you? You will have very sore toes and very sore feet, and if you are trying to head that ball, not a good idea. In that case, we want a light ball, and it must be smooth and elastic, and it shouldn't have spikes. Okay, 2 balls, different purposes, different functions, different shapes, different weight, different material. Here's another example of shape. We know that a square wheel, like this one here, wouldn't work nicely on the car. It will be a very bumpy ride. And in fact, this flat surface will even stop a lot of cars from starting. They wouldn't even be able to drive 1 centimeter. So we want round wheels that can transfer very nice and smoothly. But if you have a road that is very specifically designed like this, and the radius is right, you won't believe it, but then the square wheel will give you a much smoother ride than a round wheel, because the round wheel will go inside, kadum, 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 over these speed humps, where the square one rolls smoothly and the corner will go into that hole and so on. If you don't believe me, go and Google square wheel bicycle. There's at least one of them that exists overseas in the university, and you can get on it and you can ride it. There are videos on the internet that shows you that square wheels can work, but they need a special road. So once again, it depends on the context. Nice, smooth, flat road, round wheel. Specially designed speed humpy road, square wheels. Okay. These examples are just trying to illustrate to you that you need to understand the hazard, the characteristics of the hazard, where you are using it, how you are using it, what is it supposed to do, and then you will be able to determine whether this is a good characteristic or if it presents a risk to you. Context is important in hazard identification, risk assessment and control. Again, it means the background or the circumstances related to this activity, to the task, the area, and whatever is, the background and the environment in which we are performing our work and our activities. If you look at a hospital, a nursery school, or a creche where we put the small children while the parents are working, or a building site, or a heavy engineering factory where they're making heavy steel stuff and there's molten material all over the place. All of them present different hazards, and all of them have different cranes and pieces of equipment. You can have mining as a small miner somewhere in a small holding and you are washing with a pan for gold, or you can go into these large open cast mines where they've got 500-ton trucks. Both of them are mining operations, but their character is very different. Now, let's talk about energy transfer. Closing potential is one characteristic that a hazard needs to have to cause harm. The second one, and that's the more important one, is that energy transfer. Now, what is energy? Very generally, when we talk about energy, it's the ability to do work, the ability to change something, whether you change position, whether you change the physical characteristics or the shapes. Energy is the ability to do work. When you get up in the morning and your energy has been consumed, or you're not feeling very healthy, or you haven't eaten enough, or you haven't slept enough, your energy levels are low and you don't feel like working. You are not very enthusiastic and you are probably not going to have a very productive day. So if you don't have a lot of energy in the morning, you will not be able to do much work during the day. But other days you get up and you are all sprightly and bright and full of energy and you just want to go. On that day, you are probably going to get a lot done. So that's energy, the ability to do work. Of course, the more energy you have, the more ability you have to cause harm. All right? So the work that we're looking at is not just good work, useful work. We're also going to identify the potential to do harm when that energy is uncontrolled. Just think of young children that are playing in the house and they are full of energy, but they don't control themselves very well. It's very nice for them to play, and then they run into a table and they break your crockery, your glasses, or they run into the TV or something like this. Okay, then that energy that they had has turned into harmful work. Now, there are many ways in which we can transfer energy. They are all what we call physical quantities. So it has to come from a hazard, which is a physical thing. So energy must come from a hazard, which is a physical thing. Can't be a thought. Can't be it has to originate from something. Yes, a person may have to use the hazard, give it energy, or to create the closing potential. In other words, a person can bring a hazard closer to you, like a knife or something like that, or a hammer, and use that to cause harm. But he's not going to stab you to death with his finger. He needs a knife, or he needs a screwdriver or something like this. So even if a human is involved, you still need a hazard to be able to do the harm. So if I have a physical hazard, and the energy that's going to be transferred will come from that hazard through heat, electricity, mechanical movement, or something like that, I can put barriers in place that will stop that energy or that will reduce that energy. It can either stop it from getting the target, or it will reduce the energy so that when it gets to the target, it does not cause any harm. Understand that energy, once again, is not a bad thing. If we didn't have energy, we wouldn't have lights, we wouldn't have the internal combustion engine, we wouldn't have been moving, they wouldn't have had steam, we don't have. So there's a lot of energy in the world that comes from fuel, it comes from food, and we convert it using machineries in our body to be able to do something, all right? So energy is useful to us every day. But if that energy goes out of control, just for a moment, consider a car driving on the highway. It's very useful because it's got 4 people in it, and it transfers people over a long distance from point A to point B. But if that person that is driving that vehicle, if he loses control of this vehicle, and that speed and that vehicle goes off the road or it strikes something, then that energy that was transporting us from point A to point B is now very harmful, and it kills 4 people instead of getting them from one place to another one. And so there are many ways in which the energy that we have can be misdirected. Electricity flows in our wires and all over the place, and we feed them to electrical devices, and we do anything from make coffee, mix stuff, we have lights, we have TV, all of those things. But if that energy that is in those electrical cables, if they are allowed to get out of control and makes a short circuit, it will start a fire. If you touch it and the energy flows through your body to the earth, you can die. So useful energy can be very harmful if it gets out of control. Here's an example of fuel, and this is petrol. If I put petrol in this machine, it will make this thing go pa 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 pa, and it will make the wheels go round, and I can use it usefully. But if I take the same petrol and I go and put it on my fire and it gets out of control, then I can get terribly burned. I can even burn my house down or even my neighborhood down. Okay, so it's not the hazard and the energy and the hazard that is good or bad. As long as I can use the energy and the hazard in a controlled way, that's nice. So if I use an angle grinder and I can cut and I can keep it on the device and the sparks are flying and it's not touching anything that can burn, then I can use this electrical energy and I can cut through a piece of steel, can cut through concrete. But if that thing slips and that wheel contacts me on my leg, then my leg is cut off. That's not a very useful way of using an angle grinder. Or if the sparks that are flying from there flies into something that can burn, then it can start a fire. And that's not what I wanted either. Okay, so I need to see where the energy is. The hazard is the source of the energy. I need to identify what kind of energy, what kind of work is it doing, and I also identify what work is useful and what work is harmful, because I want to prevent the harmful work. Now, there are many forms in which energy is stored. We've got electrical energy, we've got mechanical engine energy in terms of tension, springs, cables and stuff that are under tension, they are loaded. We've got machinery that are turning, we've got heavy equipment that's rolling, that may be rolling out of control, a handbrake or something. We have things that can fall. Those are all mechanical energy. We've got chemical energy, fuel, chemicals, acids, powders. Food is chemical energy. And if you eat too much food, you will get fat because you are taking in too much of that energy that is now harmful to your body. All right? So food is chemical energy. Don't have too much of that. Then there's radiation, nuclear radiation. Sometimes we have nuclear scales or point source detectors, or in the construction industry, we've got these densitometers that you put on the surface to measure the compaction. There's sonic energy, sound. You drive in a vehicle or you drive in a taxi and that guy's got a veneer of a sound system. And it goes do so much so that the taxi is actually pumping up and down. What do you think happens to your ears? It's a nice thing to listen to, but that sound energy is hurting your ears and you're going to get noise-induced hearing loss. Loud bangs, if you shoot or you work with loud machinery or you hit with a hammer on something that makes a lot of noise, that's sonic energy hitting your ears, the energy from the hammer going into the steel, some of it converted into movement, some into heat, some into noise, and the noise will then harm your ears if the noise is too much. Thermal can be too cold. So if something is too cold, it will suck the energy, all the heat from your body, and you will die from exposure. If it's too hot, you will not be able to cool down and you'll suffer from heat stroke. You can even get burnt from infrared. So a fire, it's not the flame that burns you, it's that radiation of infrared. Or if you touch something that's too hot and the energy comes into your hand too quickly, you get burnt. There's nuclear energy that we used to make power and do a few other things with. There's pneumatic things, a tire that's pumped up, a air hose, an air cylinder, things that are compressed and then too much or the pressure is released in an uncontrolled fashion, and then there's a pressure explosion. Hydraulic, very similar, things that are under pressure, and if that hydraulic pressure becomes uncontrolled, then it will create a very strong, powerful jet that may hurt things. We see that when we do water jet cutting and that kind of stuff. So there are many forms in which energy can get transferred. And I can only figure out how that energy can get transferred in useful and harmful ways if I understand the hazard. So giving you this guideline on characteristics of the hazard and the energy is not just for nothing. It's for you to be able to characterize that hazard and to predict how it will behave, and then to decide what's good, what's bad, what's useful, what's harmful, and to be able to control that. Unfortunately, not all the hazards are easily recognizable as energy sources. You might have chemical substances like nitrogen, argon, LP gas, CO, and those things. That is a chemical that you will inhale and it will act on your body or take the place of something useful and therefore exclude things. And by excluding things like oxygen, it will cause harm. Sometimes there are things like bacteria and viruses and parasites and those things which we can't readily see. But they are also hazards with characteristics that can do harm. And sometimes they can do useful harm and harmful work. All right. So if I use something in a vaccine, it's a virus or something that's been modified, and it does useful work. But if a dangerous organism gets into my body, then it will kill me. Another factor to think about when we look at hazards and how they cause harm is how much energy is transferred into the target and over what time. A lot of our focus in our day-to-day safety management is on the hazards that have high levels of energy and that when it contacts the target, it's like a blood and guts incident. So we're looking at the powerful hazards that will immediately cause injury or death. And sometimes what we do is we forget about the other ones that are acting over a much longer time. So hazards that we see on a regular basis that we are normally quite aware of are things with a high force, like vehicle accidents, crane, anything with a bang and a cut and an explosion or a fall or something. It's a high force for a short duration of time that results in harm. You must also remember, however, that there are things like noise with a jackhammer. It causes harm, but you don't feel it today. It's only when you go for the next medical or when you watch the TV program and your wife says, please turn it down because it's too loud, and you say, I can't hear. Okay, the wife is a bad example because most men become tone deaf towards their wives. I don't know why is that, but you can speak to the wives and they will tell you. Just a joke. The point is that there are things like vibration, noise, that will hurt you over time. Noise will cause noise-induced hearing loss. Vibration will cause the sheaths around your veins and your nerves to thicken in order to protect them. And over time, that will go so thick that you will start losing feeling in your hands. You will lose circulation in your hands, almost like when you had frostbite, if you were exposed to cold and your hands froze. Noise-induced hearing loss cannot be reversed. You will be deaf for those frequencies forever. Vibration damage, if you don't get exposed to vibration for a long enough time, most of that you can get the circulation back and the feeling back. But those are things that we don't often know because we focus so much on the high force, short duration hazards. And then there are hazards that can even take years to cause harm and damage. Malnutrition, dust, you can get black lung, you can get silicosis. Normally, if people handle too heavy things, then their backs, the cushions in their back, in the vertebrae, gets compressed over time. And it may take years before you really see the damage that has occurred because of the way that you worked and the hazards that you were exposed to. So they are low force. You don't feel it on a daily basis. Some of them don't even make you tired. But 5 or 10 years down the line, you suddenly realize, but now I've got heart disease. I've got back problems. I might have lung problems, asbestosis, silicosis, black lung. I might even, from working with a mouse, what happens when you use your wrist like this, from repetitive movements, you also start getting things like carpal tunnel syndrome. We don't know about these things. We don't observe the hazards that are going to cause them. If I told you that a mouse, a computer mouse that we use, is going to hurt you, you would probably have not believed me. But if you don't believe me, go and look up carpal tunnel syndrome, CARPAL tunnel syndrome, and see what it's like and where it comes from. I've been talking about targets. Targets. What are the targets? Because we've now spoken about the hazards and the hazard characteristics. Let's talk about targets. A target is anything that can be harmed. Personnel, people, equipment, product, productivity, in other words, business interruption, the environment, your reputation. Those are just examples of targets, of where you can suffer because you did not identify hazards and control them. Note that one hazard doesn't necessarily attack one target. If you have an oil spill that is hot, it can burn somebody, it can catch fire, and it can harm the environment. Okay, so 3 targets hit by one unwanted energy release of the hydrocarbon. Something that I just want to bring to your attention that you need to look at when you look at characteristics of hazards. Understand that hazards do not always work independently. One hazard can cause harm sometimes to more than one target, but sometimes you have more than one hazard working together, and their harm together is even more than if they were separately. You have a fire, and you get some wind that starts fueling that fire. It starts chasing that fire. It gives it more oxygen, and it starts moving it faster and faster through a forest, for instance. Now we've got two hazards. We've got the wind, which we should see as a hazard, because that can break things on its own. It can move things on its own, although it's useful if I use it for generation, for sailing, and for other things, cooling. And I've got fire, and these two are now working together, and now I've got a big fire. If I have, for instance, another case is I have a flammable vapor. I have batteries. I have a whole lot of batteries nowadays with all of the load shedding, and so we've got batteries. And I've got batteries standing in a closed room. Those batteries are charging, and in the process of charging, they produce hydrogen gas. Hydrogen gas, because my room is not ventilated, because I don't know about the hazard of hydrogen gas coming from a charging battery, the hydrogen gas builds up. I come into the room and I switch on the light, but the light bulb is not nicely connected to the plug, and there's a spark. And the next moment, this electrical circuit and the spark combined with the buildup of hydrogen, boom, there goes me and my battery room and everything that I had. I could also have chemical interactions. Like I said earlier, if I take hydrochloric acid and I combine it with aluminium foil or copper or some of these reactive metals, once again, I can create a hydrogen gas. If I take another example is if I take a harmless chemical like glycerine that we even use to clean babies' faces, and women use that for makeup cleaning. It's a very harmless substance. It's like a gel, oily, smooth kind of thing, water-based. And if that mixes with something like nitric acid, then suddenly the chemical reaction between these two things is so violent that it causes heat and it becomes unstable. And nitric acid and glycerine together make nitroglycerine, which is the foundation of dynamite. And if I have these two things reacting uncontrolled, it's a runaway reaction, and a huge explosion will follow. So don't try and make nitroglycerine at home, all right? It's a very dangerous process. I just use this to illustrate how if two chemicals get together, they can react and create a big problem afterwards. So you will often see that nitric acid, when you look at, if you ever use nitric acid on the MSDSs or the safety data sheets, it tells you to keep nitric acid away from organic substances. But if you don't know what nitric acid is, and if you don't know what an organic substance is, how can you keep them away from each other? Therefore, you need to be able to identify your hazards so that you can keep them separately. The same thing with something like chlorine or some other oxidizing chemicals. If you have chlorine with some other materials that can burn and spontaneously combust, chlorine is the oxidizer. It gives oxygen. And if you combine these two chemicals, two types of chemicals, under the right conditions, you will have a fire happening without a match even being close by. So you need to understand your hazards. You need to understand the chemicals and the physical objects to be able to control them, keep them apart, to put barriers in place where they don't cause harm. Okay. We've covered hazards, their characteristics, the context. We've talked about targets. Let's talk about barriers. A barrier is exactly what it sounds like. Actually, we talk about two things. We talk about controls and we talk about barriers. Barriers are typically a physical construct. So it's a physical target trying to get energy in physical source of harm, that's the hazard. It's got closing potential and it's got energy. If that energy becomes uncontrolled and it strikes a target, then there will be harm. So what we want to do is we want to do two things with a barrier, if we can. The first thing is we want to stop the hazard from contacting the target. Because if the hazard cannot contact the target, it cannot transfer energy, it cannot cause harm. Or the other thing that we want to do is if the hazard contacts the target, I want to be able to absorb that energy into the barrier so that the target is not harmed. An example, for instance, is a bulletproof jacket. What they do is they've got a jacket here with a big tile plate and some Kevlar, and if you shoot at them and you hit this target, then there's some energy going into the person behind this bulletproof jacket, but the bullet cannot penetrate the steel, so it cannot break the organs inside the body. They've got a blue mark and a big bruise on their bodies from the impact, but this barrier that they had on their chest actually stops the bullet from causing as much harm as it could have. Same with a hard hat. A hard hat won't stop anything. If the amount of energy that hits that hard hat is more than the hard hat can protect you from, you will still suffer an injury. But light stuff and things that could have fallen into your head because your head is not strong enough, we put a barrier on your head that is nice, strong plastic and it's got a strong shape. And when things of a certain energy falls down on your head, it does not penetrate your head, it actually gets deflected with a hard hat. Same with safety boots and overalls and all those things. Overalls won't, and gloves won't stop you from getting hurt, especially on not kind of crush kind of injuries. But instead of your skin being the first barrier, the first thing that it will contact, it will actually touch the overall or the protective clothing outside, and it will get deflected, and the harm that happens to your body is not as much as should have happened. So that is the idea of a barrier. Now, a barrier we can put on the hazard. So, there's a dog that can bite us, so what we do is we put a muzzle on his mouth. Now the dog cannot bite me. The same with the machine. The machine has got moving parts or areas where the energy can come out of the machine in an uncontrolled fashion, or I can put my hand in there and get exposed to some of that energy of the moving machinery. So what we do is we put lids and covers and guards onto these machinery so that the energy stays inside that machine. Even if something comes loose, it will not fly out of the machine, it will stay inside. So I can put barriers on the hazard to keep the energy where it needs to belong. Another place to put the barrier is like the bulletproof jacket or a barricade or a handrail, things like that, where I put the barrier somewhere between the hazard and the target. And the last place where I can put the barrier is like PPE. That is where I actually put it on the target. So I pad the target, or I put a protective cover on the target so that when the hazard attacks, when the energy does get through, then the energy is mitigated. So typically, these kind of had the barriers that's on the target or between, we call that preventative, because that stops the closing potential. It stops the hazard from getting close enough. And then it absorbs the energy before it gets there. And then the PPE is what we call mitigating. So the energy from the hazard has already reached the target. All we can do now is try and make the impact and cause the harm to be as little as possible. Barriers are all kinds of walls, guardrails, insulation, toe boards, shielding, hard hats, barricades. And then I've got controls, which are not physical barriers, but things like procedures, training, tag out, lockout, behavior observations, inspections. Those are control measures. They don't physically stop the hazard, but what we do is we try and control the circumstances and the conditions so that the energy does not get transferred to a target. Barriers, as we say, they serve as countermeasures to prevent, and can be procedural or threat separation. And sometimes, and most of the time, what we do is we don't have one barrier in place. We have multiple barriers. So the machine is designed a certain way. It's got guards on. Then people wear PPE. And there are procedures that regulate how they get to a machine and how they lock out and isolate. And for an incident to happen, all of those barriers need to fail at the same time. So what we do is it's like wearing a belt, wearing a pair of pants and being afraid it might fall off. So you wear a belt and then you wear suspenders and you need another piece of rope that you tie. Now you've got three things that have to fail at the same time before your pants fall down. This is roughly hazard barrier target analysis. It's a good way of doing hazard identification and risk assessment so that we can control them. We'll talk about risk assessment and control a little bit later. But it's not foolproof. It's only a methodology. It depends very much on how good the people that are executing the methodology do, how well they do it. Sometimes there are hazards that we just don't see. We don't realize they're there. Things like confined spaces, which are hidden, operator fatigue, operator behavior, invisible gases, products that is the result from things like decomposition, methane, CO2, hydrogen sulfide, and those things. And then also understand that when I talk about barriers, sometimes there are barriers that we use, and if I have to put them in exactly a category, a surge protector goes on the hazard, but it also sits between the hazard and the target. Vaccines is not really a barrier on the hazard, between, or even on the target. It goes actually inside the target. Self-contained breathing apparatus is something that you wear on you, but it sits between the hazard and the target, and so on. So not everything fits very nicely in these categories, but it works for 99.9%. Just as a footnote to all of this information, because when you do a risk assessment, people are now asking me, so do I have to now put on the form whether something is large or small or this or that? No. When you look at the hazard, you will write the hazard name there and you will describe it. But when you start thinking about the incidents that will flow from this hazard, you need to be able to say that thing is large. If it is large, then so and so. It's got chemical energy. If it's got chemical energy, this and so and so. These are the incidents that can follow. So you are not going to be recording all of the details for every hazard. You're going to take the information that you are putting in your mind by thinking of all these things, all the characteristics of this hazard. And you are then going to apply your mind based on your knowledge, your experience, and your imagination and other information. You are then going to say, because this hazard is like this, therefore I can expect these kind of incidents that can happen. So it's a step that's going to happen in your mind. We're not going to write that down on paper. So we're going to do the hazard identification, a description of the hazard. Then we're going to think about this hazard and we're going to analyze this hazard in our minds and in other places. And then based on that analysis, we are then going to identify possible incidents that may result from the involvement of such a hazard in your workplace and activities. Right, so don't get confused with all this information about the character of a hazard. It's like an intermediate step that takes place in your mind between identifying the hazard and writing the incidents. But it's a very important step that needs to take place, and it's a step that we miss. We just write this and then we don't understand the hazard, and then we come up with a list of generic controls like checklists and training, but we never make sure that our controls are actually addressing the features of the hazard that is going to result in closing potential or in energy transfer.